Welcome to our deep dive into analyzing I/O wait latency, a critical aspect of system performance. Input-output, or I/O, refers to any program or operation that transfers data to or from a storage device, network interface, or other hardware. Latency, in simple terms, is the delay before a transfer of data begins following an instruction for its transfer. So, I/O wait latency specifically measures the time a process or an entire system spends waiting for I/O operations to complete. This wait time can significantly bottleneck application performance and overall system responsiveness. Imagine a busy restaurant kitchen where chefs are constantly waiting for ingredients to be delivered or for dishes to be washed. This waiting directly impacts how quickly meals can be served. Similarly, in computing, excessive I/O wait can grind your applications to a halt, leading to sluggish user experiences, missed service-level agreements, and inefficient resource utilization. Understanding and mitigating this latency is paramount for maintaining healthy, high-performing systems in today's data-intensive environments. High I/O wait isn't just an abstract metric. It has tangible, often severe consequences for system performance and application reliability. When a significant portion of CPU time is spent waiting for I/O operations to complete, it means the CPU is idle, unable to execute further instructions for the waiting processes. This directly translates to reduced throughput, as the system can process fewer requests per unit of time. For user-facing applications such as web servers or databases, this manifests as frustratingly slow response times, potentially leading to timeouts, errors, and a poor user experience. Imagine an e-commerce website where database queries take an extra 500 milliseconds due to disk I/O bottlenecks. This cumulative delay can drastically affect conversion rates and customer satisfaction. In critical enterprise systems, prolonged I/O wait can even trigger cascading failures, affecting multiple interconnected services. Therefore, diagnosing and resolving high I/O wait is not merely an optimization. It's often a necessity for business continuity and operational efficiency, directly impacting revenue and user trust. While traditional monitoring tools like TOP, iostat, and vmstat are invaluable for a quick overview of system health, they often fall short when it comes to deep diving into I/O wait latency. These tools provide aggregate metrics such as overall CPU utilization, disk activity rates, or average queue lengths, which are useful for identifying that a problem exists. For example, iostat can show you the percentage of time the CPU spends in I/O wait, percent I/O wait, and device utilization. However, they lack the granularity to pinpoint which specific process is causing the I/O bottleneck, what exact file or block device is experiencing the contention, or why the I/O operations are taking so long at a micro level. They function much like a car's dashboard. They tell you if the engine is overheating, but not which specific component, like a faulty sensor or a clogged fuel injector, is causing it. To truly understand and diagnose the root cause of high I/O wait, we need more sophisticated, high-resolution tracing tools that can peer directly into the kernel's operations and trace individual I/O requests from their initiation to completion. This is where tools like Ftrace become indispensable. Ftrace, short for function tracer, is an internal tracing mechanism built directly into the Linux kernel. It provides an unparalleled ability to observe the kernel's internal workings with minimal overhead, making it an incredibly powerful tool for performance analysis and debugging. Ftrace allows developers and system administrators to instrument various points within the kernel code, known as tracepoints, and record events as they happen. Think of Ftrace as a high-speed camera embedded within the core engine of your operating system, capable of capturing every tiny movement and interaction. It's not just for functions. Ftrace can track specific kernel events, scheduling activities, and even I/O operations at a very low level. This granular visibility is crucial because it allows us to move beyond high-level statistics and understand the precise sequence of events that lead to performance issues like I/O wait. Unlike external debuggers that might halt or significantly slow down the system, Ftrace is designed for live system monitoring, capturing data with microsecond precision, enabling deep analysis without disrupting production environments. When specifically targeting I/O wait latency, Ftrace offers a rich set of trace points within the block subsystem, which is responsible for handling block device operations. These block trace points provide detailed insights into every stage of an I/O request lifecycle. We can monitor events like block RQ issue, which signals when an I/O request is submitted to the block device driver, and block RQ complete, indicating when that request has finished. By capturing the timestamps of these events, we can precisely calculate the duration an I/O request spends at the device level. Furthermore, Ftrace can trace scheduler events, such as sched switch, allowing us to understand when a process is descheduled while waiting for I/O and when it resumes. This correlation helps determine if the I/O wait is truly due to slow disk operations or perhaps contention within the kernel's I/O queue. This level of detail empowers us to not only identify that I/O is slow, but also where in the I/O stack the delay is occurring, whether it's the storage device itself, the device driver, or the kernel's request processing. This capability is paramount for effective root cause analysis. Block tracing, at its core, involves monitoring the activity within the kernel's block layer, which acts as an intermediary between the file system and the underlying storage devices. This layer is crucial because it aggregates, orders, and dispatches I/O requests to physical disks or storage arrays. When we talk about block tracing in the context of Ftrace, we are leveraging Ftrace's block trace points to gain unprecedented visibility into these operations. Specifically, these trace points allow us to see not just when an I/O operation starts and finishes, but also details like the device involved, e.g. SDA, NVMe 0N1, the starting sector on the disk, the size of the request in bytes, and the process ID, PID, that initiated the request. Historically, tools like blktrace were dedicated utilities for this, but much of its functionality and insights are now achievable and often more integrated directly through Ftrace's capabilities. By collecting this rich metadata, we can reconstruct the journey of each I/O request, identify patterns of inefficient I/O, detect specific requests that suffer from high latency, and ultimately attribute these delays to specific applications or kernel components. This is essential for fine-tuning storage performance and optimizing disk-bound workloads. Now, let's walk through the practical steps to set up Ftrace for block tracing. The Ftrace interface is exposed through the debugs file system, so the first step is to ensure it's mounted. You typically do this with mount-t debugfs /sys/kernel/debug. Once mounted, you navigate to /sys/kernel/tracing. This directory contains all the Ftrace control files. To enable block tracing, you'll need to specify the desired events. We're interested in the block events, so you would execute echo block:set_event. This command tells Ftrace to enable all trace points within the block subsystem. If you wanted to be more specific, you could enable individual events like block RQ issue and block RQ complete separately. Before you start tracing, it's good practice to clear any old trace data with echo >trace. Then, to begin capturing data, simply enable tracing with echo 1 tracing on. Once your workload or issue has been observed, disable tracing using echo 0 tracing on to stop data collection. These steps provide a solid foundation for capturing valuable I/O latency data directly from the kernel. Once you've captured trace data, the next crucial step is to analyze it. The raw trace data is typically found in /sys/kernel/debug/tracing or can be streamed live from /sys/kernel/debug/trace_pipe. The output is a highly detailed, time-stamped log of kernel events. Each line in the trace log will contain information such as the CPU it ran on, the process name, its PID, the event name, e.g. blkRQ issue, and event-specific arguments, e.g. device name, sector, size. To interpret I/O wait latency, you'll specifically look for blkRQ issue and blkRQ complete events for the same PID and device. The time difference between these two events directly represents the latency of that particular I/O request at the block layer. Furthermore, you can correlate these with sched switch events to see if a process was put to sleep during this I/O operation. Tools like trace-cmd or custom scripts are often used to parse and summarize this extensive raw data, making it more manageable. They can calculate average and maximum latencies, identify the top PIDs causing I/O, and even visualize I/O patterns over time. This systematic analysis helps to pinpoint exactly which operations are slow and why. Let's consider a real-world scenario. A critical PostgreSQL database server is experiencing intermittent but severe performance degradation, with query response times spiking from 10 milliseconds to over 500 milliseconds. Traditional iostat shows high I/O weight, often exceeding 60%, but doesn't tell us which database query or process is the culprit, nor why the disk is slow. By deploying Ftrace with block tracepoints, we captured data during a peak load. Analysis revealed that a specific set of database write operations originating from a particular PID, e.g. PID 7890, representing a nightly batch job, consistently showed blkRQ issue to blkRQ complete latencies exceeding 300 milliseconds. Further investigation into these specific requests, aided by the sector and size information from Ftrace, pointed to highly fragmented writes to a particular logical volume. Correlating this with sched switch showed the PostgreSQL process was indeed spending significant time blocked on these I/O operations. The root cause was identified as an inefficient indexing strategy coupled with a poorly configured RAID array, leading to excessive small random writes instead of larger sequential ones. The solution involved optimizing the database indexes and reconfiguring the RAID array for better write performance. Ftrace provided the granular data needed to move beyond guesswork and precisely identify the underlying problem. In conclusion, analyzing I/O wait latency is a critical skill for any system administrator or performance engineer. While traditional tools provide a high-level view, Ftrace, combined with block tracing capabilities, offers the necessary depth and precision to identify the true root causes of I/O performance bottlenecks. By understanding how to enable, capture, and interpret trace points like blkRQ issue and blkRQ complete, along with correlating sched switch events, you gain unprecedented visibility into the kernel's I/O operations. Best practices for effective I/O latency analysis include: first, always start with high-level monitoring to identify a potential problem area. Second, use Ftrace to zoom in, focusing on specific workloads or timeframes to capture relevant data. Third, employ automated parsing and visualization tools like trace command or custom scripts to make sense of the vast amount of trace data. Finally, proactively monitor and establish baselines for I/O latency to detect deviations quickly. Mastering these tools and techniques will empower you to build and maintain robust, high-performing systems that deliver optimal user experiences, ensuring your applications run smoothly and efficiently. Thank you for joining us on this deep dive.